Welcome back. In the last lecture, we finished our characterization of the matching polytope, which we obtained from the perfect matching polytope. And now we're going to look at the dual of the matching polytope. And we're going to look at, therefore, the primal and dual problems that come from finding a max or min weight perfect matching. So it makes sense, of course, to think about a max weight matching without insisting that it's perfect, or a min or max weight perfect matching. But it wouldn't make much sense to ask for a min weight matching, because then we would just take the empty matching. Okay, so the new element that we're introducing is a weight vector. So for a weight vector W, which means the collection WE on the edges, we can define the max weight matching problem as follows. I want to maximize WE XE subject to the constraints that the previous two lectures have told us characterize the matching polytope. So I need x of delta V to be less than or equal to 1. If I set that equal to 1, I get a perfect matching polytope, and which is therefore empty if none exists. And then this constraint that for any odd subset of size greater than 3, the weight on the edges induced by that subset U of nodes has to be less than or equal to the floor of 1/2 the cardinality of U, which basically is trying to say that a triangle, a matching can only select one edge of the triangle, as opposed to putting half, half, half on all three, which otherwise would satisfy the constraint that we had and the constraints which were sufficient for bipartite matching. And also non-negativity of our weights. So now let's write down, let's call this the primal problem, and we can write down the dual problem. So the dual problem is going to have variables that I will call YV associated with the single node constraints, and it's going to have variables ZU, which are associated with all of these odd subset constraints. So again, we've got an exponential number of variables. And the dual is now the minimization problem, minimizing the sum over all V of YV plus the sum over all U greater than 3, U odd. If I don't write that, it should always be understood. I'm only going to be talking about odd subsets U of the dual variable ZU times the weight that's sitting right here on the right hand side, 1/2 U. And again, as always, I would expect that you would practice and try to make sure that you can derive this dual. I mean, I know we all know the general formula that it's the dual variables P transpose A, some relation to the cost vector depending on the constraints. But again, doing that is an important exercise. I guess I'm saying obvious things. Subject to the sum over all V in V such that E is an element of delta of V, which means all vertices. This is for a fixed E. The sum of over all vertices, the two vertices that are on the edge of E, YV plus the sum over all U odd, again greater than 3, and such that E is one of the edges in U, ZU is greater than or equal to WE for all E. And then I also need, because I have inequalities in the constraints in the primal, the Y variables and my Z variables being greater than or equal to 0. So this is a primal, and this is the dual. And our goal is to show that the dual has an integral solution. In particular, the dual not only has an integral solution, but it has an integral solution with some additional structure on its support. And this is the content of what's called the Cunningham-Marsh formula, which I'll write here as a theorem that says the following: if the weight vector is integral, I shouldn't have written WE, just the weight, so the whole weight vector. W is integral, then two things. First, I can take Y and Z, optimal dual solution can be taken to be integral. That's convoluted phrasing. I just mean there's an integral optimal solution to the dual. And then, moreover, the support of Z is a laminar family. In other words, there exists an integral vector Z that's part of an optimal solution to the dual whose support is a laminar family. Moreover, we can take, and when I say we can take, I mean there exists an optimal solution such that we can take Z such that if I look at this set of subsets, U such that ZU is positive, in other words, this is just the support of Z, is laminar. We've defined laminarity in a previous lecture, but let me just remind you, omega is laminar if whenever U1 and U2 are elements of omega, then U1 is a subset of U2, or U2 is a subset of U1, or U1 and U2 have no intersection. So let's prove this theorem. This theorem is going to operate on by induction. So the proof follows by induction on the number of edges and also the size of the weight vector. So the sum over all edges WE. So it's induction on those. So in particular, note that this implies, again, if I skip the base case, it means it is very simple, and I encourage you to think of it. So thus, this means that we can assume, without loss of generality, that my weight vector is at least 1 everywhere. We know it's integral. And all this is saying is that it's not going to be 0. Otherwise, I could just simply omit that edge and then appeal to the inductive hypothesis. And now here's an exercise. The exercise is to show that if there exists a vertex that is present in every max weight matching, then we can use this induction to solve the problem. So the rest of the proof is going to assume that there does not exist such a vertex. So as an exercise, show that we can apply the inductive hypothesis if there exists a vertex v hat in V that is present in every max weight matching. This, again, now is part of our arsenal. If you've got a matching problem, induction, of course, is a natural concept with graphs. We've seen induction on in various different ways. Induction on the nodes, induction on the number of edges. Here we have something different, induction on the number of edges plus the total weight. And furthermore, this concept of, when we're looking at matching, of asking, is there a vertex that must be covered in every maximum size matching, here maximum weight matching, and if the answer is yes, then it provides us a basis for induction. Previous proofs have been rather simple. We just showed that removing that node yielded a graph whose size of maximum size matching was 1 less, and therefore it was easy to appeal to induction. Here it takes a little bit more thought, but it is a very similar idea. Again, note that we do not have induction on the number of nodes. As always, on inductive proof, you need to be able to use induction on the smaller subset and then create from that the kind of structure you're looking for on the large one. So I'll leave this as an exercise. But what this means for us with this exercise complete is that we can now assume that for any vertex V, there exists a maximum weight matching that does not cover V. So therefore, we have left to consider graphs G and weight vectors W such that for any vertex V, there exists a max weight matching M that misses V. And now we're going to get to use complementary slackness and we're going to see the power of linear programming in linear programming duality. One of the main themes of this course, combining those tools of convex optimization and duality, and therefore complementary slackness, which essentially, its generalization is KKT, to combinatorial thinking. So the claim is that this implies, remember our dual variables were y, I had yv for every vector, and then zu for every odd size subset of cardinality greater than or equal to 3. This implies that yv is equal to 0 for every v. In other words, y is actually a identically 0 vector in an optimal in any optimal solution. And therefore, I only need to worry about z. So why is this? Again, it's a simple consequence of complementary slackness. And let's recall, what is the constraint of dual variable yv? It is the constraint that x of delta of v is less than or equal to 1. In other words, 1 minus yv times 1 minus x of delta of v is equal to 0 for all v from complementary slackness. And again, this has to hold. There's no pairing between y and x. Complementary slackness tells us that if y is any optimal solution in the dual and x is any optimal solution in the primal, this has to hold. But what we've just claimed is that the only cases that we care about now are the cases where there is an optimal solution x corresponding to a maximum matching that misses a particular v. So let's see what that means. If it misses a particular v, it means that this is not 0, and therefore yv has to be equal to 0. So that concludes that portion of it. So all we need to worry about now is the z variables. So we're going to now use a technique that we saw also for in the lecture on R arborescences. So we're going to choose an optimal dual solution Z that, in addition to being optimal, maximizes this quadratic objective that we've seen before. Maximizing the sum, again, the sum over all u cardinality greater than or equal to 3 and odd, ZU times the floor of 1/2 cardinality of u squared. And let's let omega be its support of that variable, of that dual optimal solution Z. So again, this is all u such that u is bigger than 3 and cardinality is odd and ZU is strictly greater than 0. So the claim is that, as promised in the theorem of the proof, omega is laminar. Let's prove that. That's the next part of the proof. And we'll prove it by contradiction. Suppose claim is false. Then I can find two subsets, u and w, that are part of omega, that have non-zero intersection, and also neither one is contained in the other. So u is not contained in w. I'll just write it compactly like this, which is not contained in u. Okay, so now let's see why this has to be false, and we'll conclude this, and then we'll see that we're actually quite close to proving the main theorem. So let's go back to complementary slackness. ZU and ZW are strictly positive. This is by assumption. This is why u and w get to be part of omega. Omega is a support set. Now, what are the z variables? These are the dual variables of the constraint that x of EU is less than or equal to the floor of 1/2 cardinality of u. But if ZU and ZW are positive, it means I must have equality here. 1/2 u. And similarly, x of E of W has to equal the floor of 1/2 w. And again, this is by complementary slackness. And again, this holds for any optimal solution x. And in particular, that means it holds for any maximum matching. So let's look at what u and w look like. So here is u. Here is w. This is what we want to disprove is the case. We're saying they're not nested, and there's at least one element in the intersection. Maybe there are others, and possibly u has additional variables, and has additional vertices in it, and also possibly w. So let's see what the previous claim will give us, and the fact that that we have complementary slackness here. So let's look at a particular element, say this one. Let's look at v hat in the intersection of u and w. We know that there exists something in the intersection, and let's let M be a max weight matching that misses that v hat. Again, we know that such a max weight matching has to exist by our previous claim. So let's look at the consequence of this and this complementary slackness. If x corresponds to this matching, so let M be a maximum weighted matching, and let X correspond to M. X is an optimal solution, and therefore it satisfies complementary slackness. These complementary slackness conditions that we've written up here, when X is a matching, in other words, X is just a collection of edges, are even easier to understand. The first one is telling us that the number of edges in U that are the matching is exactly equal to half the cardinality of U. So you may have wondered, again, is exactly equal to the floor of 1/2 the cardinality of U. We know that both U and W are odd. You may have wondered why I wrote odd variables for each, odd number of vertices for each one, but of course that's why everything has to be, we're only considering subsets that are odd. But then how many, and then what this constraint, what the condition that V hat is not covered by the matching tells us is that every other vertex in U has to be covered by an edge in the matching. So I'll just do it at random here. I mean, it could be something else, obviously, but all of these must be paired by, and not paired outside. Right? So again, the point is that complementary slackness forbids this situation. Because if I had that situation, then I would not be satisfying these two constraints here with equality. Whoops. So this is what it looks like, and in particular, what this implies is that the cardinality of U and W, this intersection, has to be just like I drew it. They have to intersect in an odd. It has to have an odd intersection. It couldn't be. It couldn't be anything different. The intersection has to be odd. Okay, so now what we're going to do is the following. Let's let, and because it's odd, we know that U union W is odd, and the intersection, of course, is odd. So note again, this does not have to, in general, be the case. If I take the union of two disjoint, odd-sized subsets, U and W, it doesn't mean that their union might be even, but that's not going to be the case here because their intersection is odd. And in particular, what that means is that I can look at variables corresponding to the union and the intersection. So now let's let alpha equal the min of ZU and ZW, and again, by assumption, U and W were in the support of Z, so whatever this min, it is strictly positive. You should again be thinking what's going to happen here. What is the contradiction that we want? And you should be thinking of how we chose Z's. So Z is not only an optimal solution, but it also maximizes that quadratic. So that's where what we're going to show is violated. And what happens if we decrease ZU and ZW by alpha, and we increase ZU intersection W and ZU union W? Again, just to belabor the point, this is why we needed to show that the intersection of U and W is odd, because that means that the union is odd as well, and I can talk about these variables. Otherwise, there is no variable Z, U, union W if that were even. And increase this by alpha. And you can easily check that this is still feasible. This new solution is still feasible. Also, it's still optimal because the objective wasn't changed. The objective value is not changed. However, I have now increased, but we increased the value of this quadratic objective, the sum of ZU with the new variable ZU. I could have put a tilde or something like that, but I think it's pretty simple enough to track. And this proves the claim. This proves the claim, which again says that omega is laminar. So now let's use this to wrap up the Cunningham-Marsh, the proof of Cunningham-Marsh. Okay, so well, what does Cunningham-Marsh say? It says that z and y are integral, and the support of z is laminar. We already know y is integral because it's all zeros. We already know that the support of z is laminar. We just have to show it's integral. So let's suppose it's not. Suppose z is not integral. Then let's take the inclusion-wise maximal u hat in the laminar family. Remember what our laminar family looks like this. There is one of these is at least one is non-integral, and I'm going to take the one that's inclusion-wise biggest that's not integral. That doesn't mean that I'm going to take the outside one. Perhaps the outside one is integral, and I have to take the one inside. But nevertheless, there certainly is an inclusion-wise maximal u hat that is whose corresponding variable z u hat is non-integral. Now, in the picture that I drew, if this interior one that the remaining arrow is pointing to is non-integral, you see that it has some subsets, but it may not. But it may or may not have subsets. So let's, in any case, let's let u1 to uk be the inclusion-wise maximal subsets of u hat. Note, there may be none. So possibly k is equal to 0, and we'll see that that's fine. So z u hat is non-integral. In particular, it's also strictly positive. So let's now let alpha be that non-integrality part. In other words, let alpha be z u hat minus z u hat floor. Okay, so this is strictly positive, again, because z is assumed to be non-integral. And now let's consider what would happen to the solution if I rounded down z u hat and rounded up, not rounded up, if I round down z u hat and then I add that balance to all of the subsets z u I. So in other words, consider new solution. I'll put tildes on here just to help us. Z tilde u hat is going to be u. Let me make the hat a little clearer so now that I'm introducing a tilde. This is the hat. Z u hat minus alpha. This is now integral. And also for each I, if there is any, again, possibly there are none of these, I'm going to let it equal ZUI plus alpha. So what are the things we need to check? We need to check to make sure that this new solution is feasible. And then I want to check its objective value to see if we have a contradiction. So remember, for feasibility, we have no y. We don't have to worry about those. We just need to check for feasibility that let me show you again the LP here. So we basically have this constraint here for feasibility, and of course non-negativity. So non-negativity is certainly satisfied. So z tilde And it goes without saying that all other z's are just inherit the same value. So this allows me to complete the solution z tilde. Z tilde is certainly greater than or equal to 0. And also, so I'll check. And also, you can see that the sum over all u such that e is an element of u, and again, u is odd cardinality greater than or equal to 3, z u tilde greater than we for every e. This is maintained by the integrality of we, even if k is equal to 0. So in the event that k has, in the event that there are no subsets, k equals 0, I rounded down zu, but then that's completely fine because we was assumed to be integral. So there's no issue there. But now let's look at the objective. So our objective is the sum of z u tilde times 1/2 cardinality of u, the floor of that. And my claim is that this is decreased. And why is that? This is decreased because of this weighting. So if we look at what this weighting is doing, it's counting the cardinality, and I decreased zu, but zu hat, but I increased all of the zui's. So you may be concerned that perhaps I increased it, but that's not the case because of laminarity. So by laminarity, and because all of the ui's were taken to be inclusion-wise maximal, what does that tell us? That tells us that they are, in particular, disjoint. And therefore, this weighting exactly provides for the situation that we want, namely that this value is decreased. And that concludes this proof. So as an exercise, you can show that a consequence of so let's actually wrap up. So what is the conclusion here? Are that, first of all, there always exists an integral dual solution with laminar support. That's exactly the statement of the Cunningham-Marsh formula or theorem. But it also means that the original system is TDI, total dual integral. And this duality relationship, I'll let you show, is a generalization of the Tooth-Berish result that we had derived, in fact, directly several lectures ago. So I'll write this as an exercise. Use this result to obtain the Tooth-Berish theorem. Next, we are going to talk about the weighted matching problem and an algorithm for that uses laminarity but uses the framework of primal dual. So this will be the topic of the next lectures.